Hello everyone and welcome to another video lecture in trigonometry. Today is a practice video for trig identities. It was narrowly requested over notes by my students at the University of South Florida in order to give them a few more example problems, especially some trickier example problems that we weren't able to do the day we lectured on this material. Since it's a practice video, it is going to be a slightly shorter video than a full lecture. Also, there are some things I'm not going to cover. Basic identities like the Pythagorean, the reciprocal, the quotient, and the even-odd identities, I expect you to know going into this video. If you don't know them, that's okay. Pause, go find those identities, and freshen your memory on them before we do anything else. That way you can at least follow my work. Second, speaking of work, if you are going to be watching this video, do yourself a favor. Try the problems before I do. Pause the video. Then start the problem, try it yourself, and compare your work to mine once you're all done. That way you not only practice the material yourself, you also get some feedback while it's going on. I think that's probably one of the ideal ways to handle this. So saying, we're going to begin this exercise right here, number 60 in our textbook on page 472, and it's a standard verify the identity sort of problem. Remember that I can't work with the full equation as it's written here. If I do that, I run into logical problems. I can only really work with either the left or the right-hand side independently. Sometimes people will work with both sides separately from one another and simplify them both independently but side by side. None of the exercises that I'm going to introduce you guys to requires that. So I'm just going to pick one side. In particular, I'm going to pick the left-hand side. To me, the left-hand side seems to have more information to work with, so I'm going to note which side I began with by writing LHS. I'm going to then write the left-hand side down, and I'm going to start looking for options. Since I have a fraction, the best bet is I'm going to have to change the representation of the fraction without changing its value. And since the denominator is a sum of two terms, it makes me think I'm probably going to be using a conjugate. Or, to use the standard terminology from algebra, I'm going to use the difference of squares property. I'll multiply the bottom by 1 minus sign to go along with the 1 plus sign that I see in the denominator. And to keep things equal, the top also has to be multiplied by 1 minus sign of x. Now when I do this, I'm going to get the following result. The top will be cosine times 1 minus sine. You'll notice I have not distributed yet. My recommendation is don't do the distribution too quickly. Start out, see what you get, and then you may have to distribute afterwards. And the bottom, thanks to the difference of squares, should be the first term squared, or in other words 1, minus the second term squared, which we write as sine squared of x. 1 minus sine squared of x is going to be useful to me for the following reason. Since I know that cosine squared plus sine squared equals 1 is an identity, the Pythagorean identity, I know, among other things, that this is an equation, and equations can be manipulated. So what I can do is I can take this Pythagorean identity and I can manipulate it by subtracting sine squared from both sides. If I do, the left-hand side will simply be cosine squared, but the right-hand side will become 1 minus sine squared. Notice I have changed the way the identity has been written, but it's still the same identity. This is useful to me now because I have 1 minus sine squared in my denominator I'm working with, and according to my rewritten Pythagorean identity, 1 minus sine squared means cosine squared. So now what I can do is I can take this fraction, I can keep the top exactly as written, but I can change the bottom into cosine squared. This makes the fraction a little bit easier to look at, and now it also shows me that the top and the bottom of my fraction have common factors. Specifically, it looks to me as if both the top and the bottom have a factor of cosine of x. I can simplify that out. Get rid of a factor of cosine of x up top, which gets replaced by a 1. Get rid of a factor of cosine of x in the bottom, meaning the bottom becomes just cosine of x. And now we have a slightly different fraction. The fraction should be now just 1 minus sine of x over cosine of x. When I have addition or subtraction inside of a fraction, I can always rewrite that fraction using linearity. So, instead of all this over top of cosine, it'll be the first term over top of cosine minus the second term over top of cosine, and thanks to the reciprocal identities and the quotient identities, we now can rewrite this. 1 over cosine of x becomes secant of x. Sine over cosine becomes tangent. And would you look at that? That's exactly the right-hand side. So now, to show that I have reached the right-hand side as promised, I simply write RHS. You don't have to write LHS and RHS exactly the same way I've written it here, but I like to use this because in my notes it tells me I started on the left, I wound up with the right, here's how I went about it. Makes my notes a little bit easier to follow. All right, let's have another one. This is number 64. We're verifying another identity, and it's a significantly more ugly one. You'll notice that the left and the right-hand sides are actually pretty similar. I could choose to work with either one. You guys make your own decisions here, but personally, I usually work with the left-hand side if I could use either one just as well. Now, a lot of folks will immediately leap to the assumption that if I'm working with things like cotangent, I ought to go ahead and rewrite cotangent using the quotient identities or the reciprocal identities. I recommend not starting there. Actually, as I'm looking at this fraction here, it appears to me that once again we're looking to rewrite a fraction to make it easier to work with, and we could use a conjugate. So that's exactly what I'm going to do. I'm going to multiply by the conjugate, which would be cotangent minus cosine, which means, of course, I'm obligated to do the same to the top. Another advantage that I see working with this is that the top of the right-hand side should be cotangent minus cosine, so that gives me a clue that I'm probably doing this in the right way. I'm also going to go ahead and skip a line. So let's say equals ... and let's go ahead and put the equal sign down here. Once again, I'm not going to multiply all the way through on the top. That is, I'm not going to distribute into the parentheses I'm about to put up. I recommend you also avoid doing that, at least to begin with. And the denominator, woof, this is a long one. The denominator, first piece squared, cotangent squared, minus the second piece squared, cosine squared. Now, at first glance, apart from the fact that we've put cotangent minus cosine into the numerator, which is something we want, it doesn't look at once as if we've got a much easier thing to work with. When you get to a situation like this, and you've made the obvious first step, or, I suppose obvious is fair in this case, when you've made a good or an obvious first step and it doesn't seem to have done anything for you, the next thing you can do is start using those quotient identities I talked about a moment ago. So let's do that. I could do it to the whole fraction, but in this case, I think the part that I really want to work with is just going to be the denominator. I'm hoping, because the top already has this cotangent minus cosine part, that maybe I can simplify the denominator, and then by doing so, I'll get a clue about what to do next. So, cotangent squared, well, cotangent really means cosine over sine, so that must be cosine squared over sine squared minus cosine squared. And now all of a sudden I see an opportunity. Both of these terms in the denominator have a factor of cosine squared. Let's factor it out. Let's see if that makes things any easier. Went a little bit off screen for that one, so let me just scroll down a bit. There you go. You can see the difference between what I wrote before. All I've done is pull cosine squared out of both of these terms, put it on the outside, and now I've surrounded these terms in parentheses to indicate the distributive property. This certainly looks a little bit easier, so now what I can do is I can work inside the parentheses. It looks to me like what I should go ahead and do is combine this fraction and this 1, so I'm going to modify the 1 just a little bit. Specifically, I'm going to look at this as 1 divided by 1, and I'm going to multiply the top by sine squared and the bottom by sine squared, so that way I haven't changed the value of this fraction, but I've got a common denominator. And if I do that, then the result should be this new combined fraction inside the parentheses. And this is where I start to realize we might actually be onto something. We already know that 1 minus sine squared is equal to cosine squared. Once again, that's thanks to the Pythagorean identities. So what I can do is I can rewrite this to be about cosine squared up top. And now I have something that's primed for the quotient identities. We already said cotangent is cosine over sine, cotangent squared is cosine squared over sine squared. That's exactly what I have here. So now I can take this fraction once more and rewrite it to be about cotangent squared again. It's a lot of steps to get to this point, but it's all worth it, because now I'm looking at a numerator and a denominator that once again have common factors. Specifically, we have a common factor of cosine between the top and the bottom. So I'll get rid of 1 from the top and 1 from the bottom with these results. Then I have a common factor of cotangent between the top and the bottom, so I'm going to get rid of that with the following results. If I simply follow through on these simplifications, then it appears that the top is going to be, let's see, 1 times, okay, so the top is just going to be cotangent of x minus cosine of x, which was the top we were hoping for. Fingers crossed, that means we did our work well. On the bottom, we have cosine times cotangent left over. And scrolling back up for just a moment, that is indeed exactly the right-hand side that we were hoping for. So I'm simply going to go back down to the bottom and, as before, indicate that I'm finished by writing this is the right-hand side. Whew. That was a long one. The next one's not going to be quite so long. Moving on to that not-so-difficult problem, we're going to verify another identity. This is number 70 in the book, and I've picked this one for a very specific reason. There is an identity that we're going to use here that's not as commonly seen anymore. Specifically, it's one having to do with the top of the left-hand side, so I'm introducing this here to give everybody a little bit of practice on that one. I think that should also serve as a fair warning. I do intend to work with the left-hand side again, so let's go ahead and get that left-hand side written down. There are some things here that are a little bit easier than others, so let's go ahead and start with the easy stuff. Specifically, let's start with the denominator. The first thing we should do is make a rather obvious little observation. Said observation being that whenever I talk about sine to the fourth and cosine to the fourth, I can actually choose to write them a slightly different way. Specifically, I can write them as sine squared of x raised to the power of 2. It means exactly the same thing as sine to the power of 4. And, of course, we can do the same thing with cosine to the power of 4th. Since we've rewritten both sine to the 4th and cosine to the 4th in this way, we are now able to use the difference of squares again, and so we can write it out a little bit differently. By the difference of squares, we should be able to now write the denominator as the first term squared plus the second term squared. Some of you may already be yelling at your screen, I know what that's going to become. I bet you do. Good work. Times sine squared minus cosine squared. Ugh, we're almost off the screen. Dude. And I guess we better go ahead and extend this fraction bar as well. Now, going back to what I said a few seconds ago, some of you probably realized this first pair of parentheses, it's begging for us to use the Pythagorean identity. We already know that cosine squared plus sine squared is always equal to 1. So I don't really need that factor, and I can rewrite the denominator without it. In which case, the top is still sine cubed plus cosine cubed, the bottom is now just sine squared minus cosine squared, and we can use the difference of squares once again. Okay, so the top hasn't changed, the bottom becomes first plus second, sine plus cosine, times first minus second, sine minus cosine, and that's about all that we can do with the denominator on its own. We really can't simplify either of those two factor packets down any further, so now is when we're going to have to take the top into account. And for this, we're going to need an identity, again, one that's not seen as frequently anymore. I'll go ahead and write it off to the left-hand side, and I'm going to write it using A's and B's. So it goes something like this. If I have a cubed plus b cubed, I'm actually able to factor it. If it was a squared plus b squared, we would be done, unless we're really lucky and we're working with a squared and b squared, meaning sine squared and cosine squared. With cubes, that's not the case. It turns out that we can always rewrite a cubed plus b cubed as a plus b times a squared minus ab plus b squared. In other words, when I take a thing cubed plus a second thing cubed, we get first thing plus second thing in parentheses times first thing squared minus first times second plus second squared. In our particular case, a and b are going to represent sine and cosine. So I'm going to simply apply that information directly. Instead of sine cubed plus cosine cubed, I'm going to do first plus second. In parentheses, first plus second. Then I'm going to multiply that by the first squared minus the first times the second. I may as well go ahead and do it in the order sine cosine. And then barely on the screen, plus cosine squared. Woof, you thought the previous step was bad. Once we've gotten it to this point, we can simply draw our fraction bar and then copy our old denominator. Yikes. I don't know about you guys, but just looking at this, I would like to maybe make the top and the bottom a little bit smaller, and I can see I can do that because the top has a factor, sine plus cosine, and the bottom has the same factor, sine plus cosine. So let's just go ahead and cross that factor out of both the numerator and the denominator, which will immediately give us an easier fraction to write. Oh yeah, that is much, much better. The next thing I'm going to do is I'm going to make an observation. As I'm looking at the fraction here in front of me, I notice that the top contains sine squared and cosine squared, and they are being added together. The middle term's being subtracted, but I'm adding sine squared and cosine squared, so that tells me that I can use the Pythagorean identity again and combine them to get 1. So I'm just going to go ahead and do that. come down here to the next line and write, okay, sine squared plus cosine squared, that's 1. Then we still have a subtraction involving sine times cosine. And then I'm going to divide by, sine minus cosine. And once I finish writing this, we may as well go ahead and check back up top to see where we are compared to where we want to be. So I take a little stroll up top, and I see that the right-hand side we were supposed to get is 1 minus sine cosine divided by sine minus cosine. Oh, hey, that's exactly what we have. Fantastic. So I can simply end this problem, and our suffering along with it, I hope, by writing this is the right-hand side. We're all good to go. Now, before we depart this problem, since this decomposition, the sum of cubes, is unfamiliar, let me go ahead and also list one other important identity that looks very similar. There it is. The first is the sum of two cubes. The second is the difference of two cubes. And you'll notice the breakdown is very similar. If I'm doing a difference of two cubes, the first factor should be a minus b, and then we should get a squared plus ab plus b squared. If we do a sum of two cubes, the first factor should be a plus b, then a squared minus ab plus b squared. Very, very similar breakdowns for both of them. This isn't something that you're going to use super frequently. However, it is one of the well-known identities from algebra, and I want to make sure I include it here so you know about it. That way, if you see something that involves the sum or difference of two cubes later, you have a place to go back to recall what to do with it. All right, last one. We didn't get a chance to do much of these sort of problems, the substitution problems, so I want to make sure I cover another one. This is number 86 in the textbook, and it says we're going to complete a substitution making an assumption. We'll come back to that in a second. The expression we're going to be working with is x over the square root of x squared plus 5, and the substitution we're going to make is we're going to let x be root 5 cotangent of theta. Before we start working, let me go ahead and point out the reason that we care about this assumption that theta is between 0 and pi over 2 is that if theta is between 0 and pi over 2, it must be in quadrant 1. That way, we know every single one of the trig functions is going to be positive. This is important because if we do our substitution correctly, the inside of the square root should simplify down to be just one trig function, maybe times a number. That way, when we take the square root, we don't have to worry about whether we're taking a square root of a positive or a negative. We know, for sure, the square root is going to involve only positive trig functions because theta is in quadrant 1. Okie dokie. Let's go ahead and get this party started, and we're going to do that in the simplest possible way. We're simply going to do the substitution indicated. So, x is going to be root 5 cotangent of theta, and instead of x squared here, we may as well just go ahead and square this. If it helps, you can always write underneath what happens when you square it. So if I square, I should be squaring everything here, so I'll square root 5 to get 5, I'll square cotangent to get cotangent squared. Not strictly necessary, but if you find it helps, go ahead. So I'll be writing 5 cotangent squared of theta, whoops, I know what that was, plus 5. Maybe the machine is also excited. Don't worry, machine, we're all excited here. Okay, now, if we do a substitution like this, it's because we anticipate being able to simplify something, and I'm looking for opportunities to simplify. On top, I don't really see any opportunities. But on bottom, there may be an opportunity. I'm going to go ahead and do a little bit of factoring, which may help make the opportunity more obvious. It's going to seem almost like an inconsequential little simplification or rewrite, but it's actually going to be very helpful, as you'll see in a second. I'm going to factor 5 out of both of these terms inside the square root, which should leave me with 5 times, in parentheses, the cotangent squared plus 1. Now, you may be wondering to yourself, why is this any better? But if you are, go back to your Pythagorean identities. If you recall, one of the versions of the Pythagorean identity is that if I take cotangent squared and I add 1 to it, the result is going to be cosecant squared of the same angle. This is the identity that we're going to employ here. So when I go down to my next line, most of this is going to remain the same, but now I'm going to be writing 5 times cosecant squared inside the square root. And now I can go ahead and take a square root. Remember what we said before. Theta's in the first quadrant. So if I want, I can take a square root of the denominator if an opportunity presents itself like it's doing right now, and it won't cause any problems with my calculations. If I do that, the top remains the same. The bottom is going to turn into, excuse me, let me change that color properly this time, the square root of 5 times, well, just cosecant. A positive number, since theta's in quadrant 1. Okay, now at this point, we need to do a little bit more simplification. One piece of simplification is very obvious. Since there's a factor of root 5 on the top and on the bottom, we may as well go ahead and cross out those common factors. They're simply going to reduce to 1s, and they're not going to be important for what we do from this point onward. However, I don't know what cotangent over cosecant is off the top of my head, and frankly, I don't want to have to calculate those two things. So what I'm going to do is I'm going to rewrite both of them using a quotient identity, or a reciprocal identity, potentially. So let me see. Cotangent of theta is always going to be cosine over sine, whereas cosecant is 1 over sine. Ah, here's our opportunity. See, when we have a fraction like this one, and the bottom is also a fraction, this is called a compound fraction situation, we can resolve the division that's going on by simply taking the top of the compound fraction, which would be cosine of theta over sine theta, and multiplying it by the reciprocal of the denominator, which in our case would be sine theta over 1. Now that I've written my fraction, my division, this way, I notice that I can cross out the common factors sine and sine, and now everything is going to simplify down to just one piece, cosine of theta. And that's it. All right. Hopefully everybody was able to make their way through these exercises along with me. Everybody found that they are getting the same results as me. For my students at USF, if you're not, don't worry. What that means is you just need to work on it a little bit more. Feel free to come up and talk to me during my Smart Lab hours or before or after class times. That's all for right now, so everybody, I will see you next time, and until then, happy math.